This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Hi, good morning. How was the intro? That happened, right? Okay. I've got some handouts for you all. Hi. Anybody's got a knife? No, I was going to open this, that's all. Things have changed. Hi, how are you? Everything good? I've got that working. The microphone there is working.
Yeah, if you could just
This
use the
bit?
microphone, yeah. Because I think the lectures are recorded, so
Yeah, if you could record one of the lectures, you'll be fine. Both identical. So when to turn this on to record, do I just? Oh, it's already recording.
sorry, no, it's all connected. Sorry.
Okay.
Just
so
as long as you're speaking to the microphone, it will be recorded.
Yeah. So let's put this one here. Hopefully, and that can go.
And has everyone put their hand up?
I'm handing them out, but I don't know if everybody's here. program very good. Very good. He's probably retired. So this is the bed.
We have to see the actual drawing.
You probably know.
We don't see the demonstrators. I'll say we'll see it.
Thanks all for coming. I'm still waiting, so I got the microphone getting away hopefully. There's supposed to be about 30 people, so you just wait while you can have it browse through. I haven't used this whiteboard since the last time I lectured this week in September last year, but if there are questions to be done, I'll be happy to do that. In case you're wondering, you're wasting your time here, hopefully not. I will try and revise all of Unit 3, and in September, all of Unit 4. I can't tell you if I'm a VCSSer this year because you're not supposed to, but I've been a VCSSer for the last 20 odd years and published some books as well. Obviously physics, workbooks, for HSC, IB. And I just returned late last night, so I got a bit of a jet lag. I went to a lecture tour to Singapore and Japan, and I've got a sabbatical coming up, so I'm in residence 6 months at MIT. So I do have a life outside stuff college where I teach. So I hope your time won't be wasted and be a good revision of Unit 3. But if you feel like you are getting really tired because we're in a chemistry building and because of physics lecture, then just walk around. Okay. I do lecture in chemistry as well, so I can't make chemistry jokes like why is a physicist teaching in a chemistry lab? It's okay, I can do that because I do work in chemistry a lot. It's just, there's supposed to be 10 more people. If you make a start, join us and then we'll see how we go. Feel free to interrupt at any time, get up, walk around, get a drink, whatever you want to do, chill out. This is physics, so you don't need to stress about things very much at all. You should have by now finished a fair bit of physics curriculum. In my class, we have pretty much finished Unit 4, so the last bit left in the APIs. So there is no term 4 as far as classes are concerned. I hope it's the same for you. You should have by now done perhaps electric power. You would have finished that. And moving on to diffraction, maybe. So in September, I'll go through primarily Unit 4 stuff and also what you can do to perform better in the final exam. Okay, that's the sort of plan we have. If you really want to know a little bit more about where physics can take you, you're very welcome to Google my last name. Apparently there's lots of my publications and books that are now made it to the internet. I have no idea, but I was told of that. So you can see some of my lectures there as well, both in podcast as well as video. And also some of my recent lectures 2 or 3 days ago have now made it to the internet, which are primarily on nanomaterials, superconductors, and one-dimensional quantum materials that I'm working on. So you can see where physics can take you. It's the age of new materials, just like in the 1960s. You had there was a silicon revolution. These days it's nanomaterials, and quantum materials, as we're beginning to call them, are extremely tiny materials doing very weird stuff. It's the best way I can describe that to you. I've got a couple of samples. This is my bag is straight out of the airplane. I didn't get a chance to unpack my laptop. But I do have some photoluminescent 3D printed supercomputers, components, made out of superconductors. I've got that with me. It's the world's first. And I've also got the world's first superconducting copper wire, which is a copper tube impregnated with superconductors that can carry current with no loss at all. And we're making very high magnetic field components out of that, going up to as much as 1,000 Tesla. So things like handheld MRIs now think that will happen in the lifetime. So these are some of the areas where physics can take you. But let's make a start and see how we go. Feel free, as I said, to interrupt at any time. I just put these there because I was bored, and this slide at the bottom is my idea of I don't know, some sort of a nerd nirvana, but that's my lab in Japan. And those of you who are doing chemistry might recognize this little tube here is it's a 20-meter vacuum beam line. That's on it we have mounted a number of mass spectrometers and things like that to do research, and that's beautifully organized. You know, that's what a physics lab looks like. And that's my campus on the outside, which is kind of boring, but that's the exciting bit there, okay? So we'll go how we go. We'll see how we go. That's what I want to cover today. The way I've made this 90-minute class for you guys is how the VCAA course is structured. So I'm not writing the VC exam, but if I was writing one, I would like to look at the course outline and base questions covering all aspects of the course. Makes sense. So this presentation today is in the same structure as the VCAA course. So I'll go through the concepts and the contents of the course, past exam. Probably the last two parts, if you run out of time, I can also work on with you in September. What gives you the best marks in a VCAA exam? These are not some inside tips or goss or anything like that. These are basic comments from the examiner's reports, which are on the VCAA webpage. So that's why I keep acknowledging the VCAA here, because I have used questions from the past exams and also the examiner's reports here. That's what the front page of the exam looks like from the 2018 exam. You should be familiar now that there are 20 multiple choice questions in part A, 1 mark each, and then 110 marks for more worded responses. And some of them could have multiple answered sort of responses. Few things here that you should be aware of. You write with a black or blue pen. Pencils are not allowed except to make a graph. And you can't use whiteout, and please don't use any other color of pen except blue or black, preferably black, because the papers are scanned and multiple marked. So if your handwriting is not legible, then you're doing yourself a disservice. I'm not saying you change your handwriting. You've got to work with what you have. If your handwriting is poor, maybe use block letters, maybe write shorter sentences, things that are clear. All those things matter. And what you also find is a little rectangle placed on the paper. You should not be writing outside that, because that part is not scanned. The reading time, 15 minutes. I won't go through all this here, but I think it's now clear to you. The SACs are supposedly worth 40%, but they're moderated against your school's QCS, GATS scores and other things as well. So I'm not familiar exactly with how the moderation works, but I don't think it's a straight 60-40 addition. So if somehow you messed up a SAC or two, I don't think it should affect your subject score as much as you might think. Okay. One example that I've given to my classes is that one of your SACs could be worth just as much as one major question of the final exam. So if you keep that in mind, if you mess up one SAC, all you've done is messed up one question in the final exam, and you could still come out with a very good subject score. Okay. Here's the first topic. The area of study, how do things move without contact? So obviously they're moving under some sort of a field, and the idea of what a field is. And to me, it's like a three-dimensional region where something experiences a force. So if you have a force due to gravity, we call it a gravitational field. Force due to electrostatics is called an electrostatic field, or electric field, and magnetic field, and so on. The fields where a force is experienced. So based on that, you can define a very basic idea for what a field is. You can quantify a field. So if you have electric field strength, it's the force per unit charge. You have gravitational field strength, which is the force per unit mass, and note the vector notation. And the magnetic field strength, which you now know, electric field strength E, gravitational field strength G, magnetic field strength B. Don't ask the logic for that. It's the force per, because you don't have a unit pole, you define that as IL. And when you get to magnetism, we can cover the reasons for that. So these are the way to quantify the magnetic field, which is Newton per Coulomb, Newton per Coulomb, Newton per kilogram, and Newton per meter, which is also known as a Tesla. Okay. Last part here, how fast can things go? That's a fascinating topic. And of course, in your topic, we have special relativity to try and make sense of how fast things can go. Obviously, not close to the speed of, well, not to the speed of light, but extremely close to the speed of light. So keep in mind the overall concept of what a field is. You also realize here that if you have a gravitational field, in this case, for example, you will find it's one directional like that. So if this is the center field lines on any object will be downwards. If you have an electric field or electrostatic field, then of course, depending upon which direction the positive and negative is, you could get something like that happening. Okay. There are many other aspects buried in here which I hope I can cover, but fields are fascinating things. What happens if you combine all three fields? There's at least a couple of experiments where three fields can be combined, and one of them is the mass spectrometer. Certainly in the synchrotron, certainly in the capacitors, we are combining all three as well. And there are some very interesting questions that can be formed on that. So here's some examples of field lines. And all of these diagrams are not something that I created. I just copied them from the VCAA webpage, and that's why I keep acknowledging them here. Can you tell me very quickly, X, Y, and Z, what these could be? What is Y, for example? Field lines going towards the center. What could be at the center that has these field lines, and what could be attracted to that? Could it be a supermassive black hole, perhaps? And things are attracted to that because very high gravitational field. Could it be a positive charge? Is that possible? What do these field lines tell us? It's the path that something would take. It's a path. They're vector field lines. That's why they don't touch or cross. Otherwise, you'd have a resultant vector. Okay, they're field lines. They're telling you where something would go. If it's a mass going in that direction, it's a gravitational field. If it's a charge going in that direction, it's an electrostatic field. And we only look at positive charges when you're looking at fields. So let's specify that again. Field lines are the path that a positive charge would take in an electrostatic field. It's the field lines that a 1 kilogram mass would take in a gravitational field. Okay? Going away, what kind of a charge would be here? Positive or negative? Has to be negative, because the positive charge is running away from it. So I think this was a question in VCAA to explain what these lines could be due to. What's X due to? This rule, remember that? It's a direction, a current. There has to be a wire carrying a current in here. And in this case, the current would be going like that, sticking out of the page. So those phrases, I hope by the end of today you'll be familiar with. Up the page, down the page, into the page, out of the page, left, right, top, bottom, south, north, etc. So this is sticking out of the page, and the field lines are going in an anti-clockwise direction. And obviously these are quite clear. It could be a north and a north pole, south or a south. No, it has to be a north and a north pole, because you're running away from it. The field lines are going away from it. Or it could be two positive charges. Can't be two negative charges. In this particular case, draw the field lines. How would you draw the field lines? You can have one complete loop on the top, one complete loop at the bottom. Field lines going from, in this case, sticking out towards the left, so this left end behaves as a north pole, and the field lines are then going clockwise around it at the top and anti-clockwise at the bottom. Okay? If in doubt, maybe copy a couple of these diagrams from your book into your formula sheet and take it to the exam. That might help you. There are many ways of determining these field lines. One way I've taught some of my students is if you have a coil, and let's say that's the coil here, carrying current this way. All right, so that's the direction of current, which you know is the flow of positive charges, not negative charges. You can look, the current here is anti-clockwise, and you can follow these symbols. If it's a clockwise current, it behaves like a south pole. If it's an anti-clockwise current, it behaves as a north pole. So the field lines are going to be sticking out here. And that tells you what the magnetic field lines direction would be. So depending upon the diagram given to you, you can determine what the different field lines would be. Is there enough light for you to see that? Do you want me to increase more light? Is that okay? Okay. I've got all these fancy controls here, but I'm just not familiar with everything. All right. The concept of field, here's some more quantification of what we have just talked about. In the case of the mass spectrometer, you do know you can combine the net force mv squared on r with bqv, and please feel free to interrupt. We can discuss things in detail as we go along. The Coulomb's force kq1, q2 on d squared between two charges, but if the charge is moving in a circular motion, then of course you can combine uniform circular motion and the field that's causing it to happen. These are the quantification of fields, which I've just put on the board there as well. A uniform electric field inside a capacitor is a topic that's been introduced only in the last couple of years. It used to exist 15, 20 years ago. So the field lines on the edges are curved, but in the middle are straight. And you get a beautiful uniform capacitor field in the middle. A very nice emerging area of physics to be used in many applications, and I'll highlight some of them during today. But what's happening inside there? Who first discovered this field, and what's the significance of that? This is the work of Millikan. Thomson and Millikan in almost 100 years ago, 120 years ago, were looking at discovering the charge of the electron. And that discovery of the charge of the electron is based around a field like that, where Millikan took some oil droplets, pushed them through here, recognized the fact that some were dropping down, some were going up, some stayed, and then based on the forces of gravitation and electrostatics, he was able to determine the least common denominator, which was in fact the charge of an electron. So a brilliant piece of work that's based around this particular concept. This equation here has been asked in VC exam the last 2 years. The electric field strength in the middle is force per charge, is also V on D, which is the voltage across the capacitance place divided by the distance between them. So depending upon where you introduce the charge, if you introduce the charge here, then that's the distance you're looking at. Okay? It's to do with the distance through which it moves up to the plate that it moves to. So it's not the distance between the plates. Be careful with that. And the electric field strength is V on D. It's uniform inside, but then if you're looking at other parameters, then you've got to control the D. That's Millikan's experiment. You can also use the satellite motion with things moving around the central mass to look at what the forces are doing there. So mv squared and r is gmm and r squared. So this concept of uniform circular motion, mv squared and r, can be applied to gravity, can be applied to electrostatics, can be applied to the mass spectrometer. Okay? That's what I wanted to highlight on this page. There are some sample questions. I've tried to put a lot of these sample questions throughout your notes just to try and bring a sense of why I'm talking about it this way. By the way, I just put this picture here for fun. This is a capacitor. You can see these two plates here. I know it's pretty messy, and you say, why would you make something as messy as that? But that's a 10 micron bar. So you can theoretically put something like 10,000 of these in a square centimeter. And that's some of the computer chips that my company is developing, and these are supercapacitors. So I just thought I'd put that there to put a sense of perspective of where things are going. So questions like, which one of the following is the closest to electrical force of the oil droplet? The force is Q times E. Going back to this very definition here, force is Q times E. That force is equal to these quantities put in there. All the interested information is given to you. So application, direct application of the equation that we just put here, force is Q times E, and force and V, the voltage, is E times D. So looking at a combination of that, 2017. There was a similar question in 2018. Looking at satellite motion, it seems like I seem to be going between electrostatics and gravity, but this is the way your course is structured. And hopefully some of you guys had your first SAC as simply motion under field, putting all of these things together. Okay? There's a lot of information here, and I'm not going to read this information. I just want to highlight things for you. These diagrams here are questions from VCAA. Quick question. Sun, Earth. What's the direction of net force on the Earth? Is it A, downwards, because gravity is always down? So if I rephrase the question, what's the force of gravity on Earth at this point? Down, because gravity is always down. That way, because the Earth is going in a tangent. Outwards, because that's the centrifugal force. I don't even know what that means. Or towards the center of the Earth, or center of the Sun. I don't remember exactly, but I think it was a fair percentage of students in the state who would answer this question as downwards, because gravity is always down. So be careful in some of these very simple looking questions in VCE. People still get them wrong because, you know, what is that thing called? The Occam's razor? The simple answer is often the right one. If the question is simplistic, it can still have a simple answer which is correct. And the simple answer is the net force is equal to the force of gravity, and that will be towards the center of the sun. Okay. Here's another question, force versus distance from the surface of Mars. Distance from the surface, this is not center to center. This equation here, when we say force is equal to gmm on r squared, r is center to center. Now this is where you should be scribbling notes if you want to. Just remind yourself, you didn't know that r is center to center. There's lots of space on these slides for you to do that. If you have a time period in the question, it's r cubed on t squared. Where did this come from? All this comes from gmm on r squared is mv squared on r. So at some stage, I hope you've done these COP calculations. If you have a calculator, you could try that now. But I'm going to try and just put a couple of things up here, which I hope your teachers have done already. So let's say if this is Earth, you are up here. The distance to the center is r. So the force on you will be gmm on r squared. But the gravitational field strength will be gm on r squared. Now if you put quantities in here, the mass of the Earth 6 times 10 to the 24, and the radius of the Earth 6.4 times 10 to the 6 squared, you can calculate what the gravitational field strength is on you. I hope you've all done it, is that right? And what do you get that answer to be? Roughly 9.8 Newton per kilogram. That's where the G value that we talk about comes from. Lots of other things you can do here. If you integrate FDR from 0 to infinity, what do you get? You get minus gmm on r, which is in fact the work done to take an object from infinity to a particular radius. What quantity is that? That's the gravitational potential energy. Now I know that expression is not in your course, but it does make sense. That's where it's coming from. How do you get kinetic energy expression from here? By putting the two quantities together. Gmm on r squared is mv squared on r. You divide by 2, cancel one of these r squares. What do you get on the other side? Half mv squared, which is the expression for kinetic energy. Okay. If you also combine v is equal to 2 pi r on t, and put that value of v in here, you will get the r cubed on t squared expression that Kepler observed many years ago. Okay? So all of these things are based around this central concept that the net force on something must be equal to mv squared on r if it is going in uniform circular motion. I know what you're thinking, the planets don't go in uniform circular motion. They go in an elliptical path. Yes, they do, and that's why these expressions that we had, graphical expressions of g versus r and f versus r, show a 1 on r squared graph. And we talk often about what does this area represent. Okay, so when you do integration, you multiply the y and the x-axis to determine what's in there. So if you multiply Newton meter, you get a joule. If you multiply Newton per kilogram times a meter, you get joules per kilogram. So this represents the energy change, whereas this represents the energy change per kilogram. And remember again, this is r. This is not the distance from the surface, from the surface of the Earth. So sometimes you might find a little line drawn here, which says that's where the surface of the Earth begins. So be familiar with that. So if I have to draw a line here and say that's the surface of the Earth, what should be the value of G here? Roughly 9.8. Okay? So you're able to track that. As you get closer to the Earth, the kinetic energy will increase. As you go further away, the gravitational energy will increase. That is a hint that maybe the motion is not circular. Okay? And in fact, there was one question years ago showing an elliptical path. This is the sun, that's the Earth going around. It's like a slingshot. The Earth gets closer to the sun, speeds up, slows down, speeds up, slows down. Okay, total energy is conserved. All right, that's a quick revision of satellite motion. Any questions? Okay, fine. What about the difference between weightlessness and this notion of apparent weightlessness? Apparent weightlessness means normal force is 0. So first statement in your response. Why do the astronauts float around in space? They're apparently weightless. Apparently and weightless. They think they are weightless, but they're not. So you've got to say both parts of that answer. They're not weightless. G is in fact about 86.7% of what's on Earth. The International Space Station is 400 kilometers above Earth. Okay, it's not that far off. Whereas a geostationary satellite with a time period of 24 hours is far, far away compared to that. And most of the satellites that we have are higher than the International Space Station. So some numbers you should be reasonably familiar with. How fast are the satellites going? Roughly 7,000 meters per second. So if you find the speed of the satellite faster than the speed of light, then you know you've made a mistake. And if you find the R value for a satellite to be less than the radius of the Earth, you know you made a mistake. But yet we see some answers like that. Okay? So punching those big or really tiny numbers in your calculators can often lead to some pretty silly errors and wonderfully creative but wrong answers. Okay. The energy of a satellite, we've already talked about that. If you want to move a satellite to higher orbit, you do need to do some work on it. Satellites often fall down in orbit because of space debris. There is friction even out there with lots of space debris. And to put it back, you have to boost the satellite again to a higher orbit. So you have to do work on it to get there. So these diagrams represent only the change in energy. They don't represent the total energy. So to take a satellite from here to a higher orbit, you have to do work on it. And at the same time, you have to give it some speed. To just launch a satellite into orbit, you just plonk it there. You don't have to make it go. So the total energy will have to be the kinetic energy plus the area under the graph from surface of the Earth to wherever you want to launch the satellite. Does that make sense? Okay. I'm sure you already know this stuff, so I don't really know you personally, but it's often that I run into you guys again, like, you know, the gentleman I met just now. He was in my class here last year. Now he's doing a physics and a maths course here at Melbourne Uni. I often come across students, you guys, 8, 10 years later. So please, you know, feel free to interrupt, ask questions. I'm not offended. Here are some worked examples, and I think I put these in your slides as well. I'm not saying this is the best way to answer, but I wanted to just show you some examples that should give you full marks if you follow those steps. Calculate the period of Europa's orbit, show your working. And VCSS shows show your working, you must show your working clearly. If the question says a diagram may help, please draw a diagram. A numerical question may help, yeah, absolutely. Do a numerical question, okay? It's a nice hint. First line should always be an assignment. So you're actually saying what formula you're using, what method you're using, area under the graph times the mass. Say that. That puts you on the right path and tells the examiner that you know the methodology you're following. And if you follow those methods, the chances are you won't make mistakes either. Okay, I've been working in physics-related areas for over 35 years now, both at high school, tertiary, and industry level. And following due process is extremely important, whether it's your VCE exam or manufacturing. And that's part of the step. Show the first line. Say clearly what you're doing, communicate somehow, then explain with numbers in it, and then the final calculation. And you might say, hey, yeah, I see your point. If I show all these steps and I make an error in the final line, then I'll get 2 out of 3 marks. Well, you missed the point. A, you won't make an error because you're showing the steps. Okay, and B is good process. You have to do it. There's no question about it. Same thing here. Put the numbers in, then do the calculation. So you see how I've substituted all the values in the final answer. And no, it doesn't take you more time. You're thinking in your head what you're supposed to do. Put it on paper. Okay? You will save time. Because when you come back to check, if you have time, you'll see that you've done the steps. So here's another question. Now that EPI in some ways to be tested in your final exam, numbers may be given to you, and then you have to make a graph and do some calculations and estimations from there. It could be uncertainty, it could be how you graph, get the area under the graph, get the tangent, quantities like that. So your graphing skills, your analysis skills are going to be tested in the final exam. Therefore, you must have a good pencil an eraser, a ruler, and maybe a protractor in case you have to measure the angle for refractive index. Now this question was from the 2018 exam. Data was given here. You had to plot r cubed versus t squared, and from there you got the gradient. You got the gradient. But what does the gradient actually mean? Now in my research, and I always advise, especially my postgraduate students, that you must be very careful with what you do in collecting the data. Once you got good data, you can make good graphs. So try and get a linear graph somehow, because then you can use y equal to mx plus c. If it's a curved graph, yeah, you can do mathematical regression and get quantities, but it's not always that easy. So what does this gradient mean? So you got r cubed on t squared is gm on 4 pi squared. If I make a y equal to mx plus c version of that, I can write r cubed is equal to t squared times gm on 4 pi squared. So it's sort of getting in the form of y equal to mx, and the gradient there is 4 pi squared of g. So what does it mean? That if I know 4 pi squared, I can then calculate the value of g. So many mathematical expressions you need to be familiar with to get it in the form of y equal to mx. A classic example is Planck's constant. Yes, you can have E equal to hf. You've done all that now, I presume? Not yet? You will. This unit 4. And that question has been asked many times in the past in VCE, because it's straightforward y equal to mx. What else could be there? Refractive index, have you done that yet? Okay, that's also unit 4. Projectile motion. There are lots of questions on that can be converted to a straight line. Okay. Any questions on this? Unit 4, please remind me. I'll go through the different uncertainties and error bars and what they mean and how you calculate them. All right? I don't think we'll have the time today. Here are some other questions. I'll leave these with you. I'm not going to trace that word for word because we won't finish everything I have. But once again, note that R is center to center. Calculate the period of orbit of Charon. Period, time period, r cubed on t squared. Straight away you've got to be thinking that. Okay? Calculate the gravitational field strength. What's the gravitational field strength? Force per unit charge. You should be, as you read the question, formulate the concept behind the question straight away. In physics, knowing the concept is vital. If you're asking me this question, what formula should I use here? You're asking the wrong question. It should be, what concept is this question testing? How do we quantify that concept? That's what the paper is based on. Okay, so the concept here is r cubed on t squared. The concept here is force per unit charge. Okay. Ratios. Lots of questions on ratios. Now here's only 2 questions from the 2007 exam, but you'll find that right across from 2002 to 2018 that you see on the VCAA webpage. Many ratio questions can be made. For example, if I have a satellite, if I have a projectile launching at 10 meters per second, how far will it go? If I double the speed, what happens to the range? And there's a ratio question. I have something doing a horizontal circular motion, like a pendulum that's rotating around like that. If I double the length of that pendulum, what happens to the time period? Again, a ratio question. All right? What happens to the kinetic energy of a satellite as it goes twice the radius from the Earth? Does the kinetic energy double? 4 times, half times, 8 times? A, B, C, D, multiple choice. Hundreds of questions can be built like that. Okay? A few years ago, I wrote a workbook for VCE based entirely on questions. I think it's called Dot Points Physics Unit 3. And something like 2,500 problems in there. And a few hundred of them were ratio questions. Okay? So here's some ideas on how you can solve ratio questions in VCE. Write down the equation, make the subject what is being asked, then sub the values in. The original algebra is where people go wrong. I hope I can show you more examples today as we go along. Here's another example of how things move without contact. This is now the case of a magnetic field, and you pass a current and it moves. Why? Why does a current carrying conductor move in a magnetic field? A current is simply a flow of positive charges. A positive charge experiences a force in a magnetic field. Because a positive charge has got its own electric field that interacts with the external magnetic field and the two fields then combine vectorially to give you the net field, and that's where the conductor is trying to align. So you can go right to the bottom of why is it that there is a force on it. It's because of vector field addition. Just to say because of the right-hand rule, no, that's just a rule to help you get to the answer. But what is the reason that the rule exists? There was one year in my SAC I put a question saying, the motor principle says that there is a right-hand rule like this, telling you that this conductor is going to move to the right, etc. But why does it? So nobody could answer that because of the motor principle. So very quickly, what will be the answer, A or B? The right-hand rule, current, field, force. So you place your fingers to the field first, much easier. Current, force will be down on JK, and therefore is going to go anti-clockwise. Correct answer is B. Now, this is where a lot of people have problems because it's a 3D visualization at times, and the calculator becomes really important. Does anybody have a calculator here? Just any kind of calculator to do it. I'll show you a really easy way to work out the torque of something, or force of something. This one, that's it. That's the beauty. You can take this to the exam, and there's your coil. And you can physically see that's the field, that's the current, the force on this will be down. And you can visualize this as going anti-clockwise. And you say, oh yeah, I'm looking from this side as anti-clockwise. It works like a charm. And you're allowed to take this. Very useful part. That part not so good. So that's really important to try and visualize very, very simple terms. What's the direction on one arm, and therefore the coil. All right. By the way, flux equal to B times A, another classic way of defining magnetic field. So we said here V is equal to F over IL, which has to do with the electrostatic or electric field. But you can also look at it as B equal to flux on A. I don't know where I put the pen, but please put that in your notes here as well. All right. And what are the units for that? This is measured in Webers per square meter, which is also equal to a Tesla. So Weber per square meter is a Tesla, so is amps for a Newton per amp meter. Okay, what is the role of the commutator? Asked so many times. But there's a second part to that question. What's the role of the commutator in a motor, or is it a generator? What question are they looking at? Please don't copy something from your formula sheet. Make sure you refer to the question, the example given to you, the letters used in the question, and describe those as part of your answer. Moving on. When do we finish? 12:30, is it? Okay. Everything that I have here is with you, so in case we run out of time, it's in there and you can read it. So, we already talked about this. I've given you some examples here. Field is going into the page. First question is what we're looking at now. Positive charge is coming from left to right. Will they go up or down? How do you determine it? Field going into the page, positive charge going this way, so force will be up. I find most of the time, starting with field, then current, then force is an easier way to go. Negative, don't try and use Fleming's left-hand rule and all the American things. We don't adopt everything American. So what you do with negative charge, assume it's positive and then reverse the direction. That seems to work for majority of our students. And here are some questions from VCAA to do that. And what I would expect you to do is maybe when you go home today or tomorrow, go through all these questions that I have placed in there as examples, and the combination of all those questions will be a nice revision of Unit 3 for you. I know you don't have a SAC on Unit 3 anymore, but if I asked you what were you doing in February 2nd week of first term, a lot of you would draw a blank. You forget there are many things happening. It's year 12, you're having fun, life goes on. Who cares what you did in term 2 or term 1 of physics? But your exam is not that far off. 14th of November will come around very quickly. So a good time during these holidays to go through Unit 3, and the questions I've placed here cover a large chunk of Unit 3 from past VCE papers, and would be a nice revision for you. So please do these, the answers are there as well. There's the capacitor that I've been talking about. Where do you use them? Or where do you use this concept That's the electric field in the middle, is voltage over D. The work done is Q times V. You know, in a circuit, a battery provides energy. Please don't say a battery provides charges. A battery provides energy. The charges going through the battery pick up energy, going through a resistor loses energy. How much energy? Q times V. So the energy that's provided is Q times V. That's why I like to put those arrows on top, so you don't confuse energy and electric field strength. A change in electrical energy, see? No vector notation, is Q times the change in voltage. In some cases, that could be equal to half mv squared. When? Like an electron gun. An electron gun, you provide electrical energy, the charges come off, Q times V, depending upon how much voltage you give, and then that can be accelerated through a field. Okay? An electron gun is a very central part of this course. Yeah, you okay with that? So Q times V equal to half mv squared. That allows you to determine the speed of an emerging electron, or through which it's accelerated. And off you go to wavelength and quantum physics in Unit 4. So a very important part of Unit 4, and I'll come back to that at that point as well. And we already talked about the parallel plate capacitor. If I had time, I would love to go through all those things, but we'll see how we go with time. So little things at the bottom are interesting questions that I often pose to my class. What's the difference between an electron microscope and a synchrotron? Both are accelerating electrons. Then what do we do with it? In a synchrotron, you bend it. If you bend the electrons, they're still going at the same speed, same kinetic energy. You have done work on it, but there's no change in energy. What happens to the energy? It comes off as synchronous light, and that's your synchrotron. Whereas in an electron microscope, you accelerate the electrons, they pick up more energy. The more energy they have, you will learn in Unit 4, shorter wavelengths they have, more resolution they have, and you can start looking at electron microscopy concepts. Okay, I do take some of my challenge students to RMIT to study electron microscopy, and we talk about that, and hopefully we'll get one in our school as well. Okay, here are some questions on the concept we have just studied. So you notice here concepts, some VCE questions for you to study at home. So here's a proton source. An electron gun could also be, have an analogy with a proton source, which is what we use in the Australian synchrotron. It's accelerated through 10 kilovolts. What's the energy it will have? 10 kilo EVs. If an electron is accelerated through 100 volts, the energy it has is 100 EVs. Okay, please write that in your notes if you didn't know that. Then it goes through a magnetic field and bends. What is the strength? V of D. What happens to that energy? Half mv squared. And once you get the velocity, Unit 4, you can convert that to momentum, hence the wavelength, hence Planck's law and all that stuff coming up. And BQV equal to mv squared. And now look at this question, just how many concepts have been combined here. 2018 exam. I thought it was a brilliant question. You've got mv squared and R combining with BQV. You've got Q times the change in voltage or increase in energy is equal to half mv squared. And then you got the electric field strength as V on D. Okay? Nice question, and similar questions have been asked almost every year. So make sure you hide the answers. You can almost block it off with a piece of paper on the right. That's the way I've written them out. And therefore you can solve the answers and check the answers. Okay. Part 2, we're going to look at AC power. This is not conceptually as tricky as what we have just done, so hopefully it will be straightforward. Why is it that you take a coil and you rotate it through a magnetic field, you get a current? Magic. Michael Faraday did that, and it was really, really interesting. Why does it do that? The basic concept is that if you move a conductor in a field, you're moving all the charges in it in the field. And if you move a positive charge in a field, it will create an electromotive force. Now, I'll try and do this very quickly here by way of a diagram to try and illustrate what might be happening. If you can't see it, tell me. Let's say there's a magnetic field in here, one of those wonderful VCW fields that are uniform here and zero on the outside. And you take a conductor and you move the conductor this way. The conductor has positive and negative charges. So you're moving the whole lot of charges to the right. According to the right-hand rule, it simply explains the concept. What's should happen? Field, current, force. So the positive charge is experience the force this way, and the negative charge is this way. And they try to migrate there if it's a conductor. So here's the way to counter that. So if you connect it up with a meter, that's a meter, you find the positive charges will now flow. That induced voltage here, EMF, is what BQV, etc. is all about. Or, if you like, NBIL. That's the EMF, voltage generator. If you connect it up with the voltage measured, so this will be positive here, negative there. But now you've got a current flowing through the conductor. That's the induced current. But what does induced current do? Forget that now. You've got a current flowing that way, field, current, force. Therefore, a force is generated to the left. So every time you push the conductor to the right, you experience an opposing force to the left. And that's Lenz's law. That's where the negative sign is coming from. Negative in physics means direction. It doesn't have to do with the quantity less than zero. Alright? So you're pushing it to the right, you experience the force to the left, you explain to you why that is. Okay? The induced current opposes the change that caused it. Look at the words I'm using. Induced, oppose, change. So every time there's an explanation of Lenz's law, why is the current clockwise or anti-clockwise? Induce, oppose, change. Because you're moving the coil this way, an EMF is induced in a certain direction, which creates a force to oppose the change which caused it. And that's the explanation of Lenz's law. The trick here is to try and use Lenz's law in the context of the question that has been asked. If you reproduce something from your formula sheet, trust me, I'm not going to give you more than 1 out of 3. If that. You've got to put it in the context of the question. I don't think, oh yeah, EMF minus N delta phi and delta T. What was the significance for that? And what are these quantities? When we say EMF is minus N delta phi or delta T, this flux is B times A. So you can either have a change in B or a change in A. And to get the magnitude of the induced EMF in the context of a slip ring AC generator, that small t time is 1/4 time period. Are you okay with that concept? Yeah? Why is it a quarter time period? Because the value you get from that is very close to the RMS value. RMS is 70, what is it? V peak over root 2, and square root of 2 is 1.4142, and 1 over 1.4142 is 0.7071. So 70.7% of the peak value. That average induced EMF is roughly that. It's about 69%. Okay, so you can use that average induced EMF instead of the RMS value. That's AC, that's DC. Stupid question, isn't it? But it's been asked many times and people still get it wrong. Any questions so far? Okay. I think I've covered all this. And there's far too many slides here than I can cover. These are your worksheets, if you like. And instead of giving you blank questions to try out here, if you had the whole day, I worked it out so you can hide the answers, try them yourself, and off you go. Okay. Question like this: what is the direction of the induced EMF in that coil? The direction of induced EMF through the voltmeter or through the coil are opposite. And once again, the lid of your calculator can become really useful. So if you take the lid of the calculator and you can keep it, I'll just go through the motion of it. So the calculator, if the coil is going this way through the field, and the field lines are, for example, into the page, so this coil enters the field, and straight away experiences field lines going in, that's the change. How does it oppose the change? It creates field lines going out. And if it creates field lines going out, using the right-hand grip rule, the current will be anti-clockwise. So very easy to follow the lid of your calculator. Simply say, enters the field, sees a lot of field lines, flux going into the page, creates flux to oppose that, out of the page, hence right-hand grip rule, anti-clockwise. As it emerges the field, just as it was getting used to the field lines, now the field lines disappear. So it gets really upset again and says, I want to go back to where I was, and the coil says, induce the field lines back to where they were into the page, and therefore the current becomes clockwise. And that's where the flux versus time graph, the EMF versus time graph becomes important. So as the coil enters the field, the flux rises. As it's in the field, flux is constant. As it emerges, the flux falls. Take the flux gradient to that, and you have yourself the EMF time graph. Suggestion for you: always draw the flux time graph first. Then you simply match method. What's the gradient of the graph? Yeah, and that's your EMF. All right, that question was asked many, many times. This, I think, is the 2018 exam. Okay. Here's another question. I think I've been through this description with you now. So what happens, how does the opposing force comes in, and how do you draw these sorts of graphs? Always draw the flux time graph first. It'll be easier to draw the EMF time graph after that. And here's more questions. Similar. What happens if you double the speed? If you double the speed, not just the EMF doubles, but the time period halves. You can show that mathematically if you like, or just qualitatively. What is the time interval between Q and R? Mathematically done, much easier. Time period is halved, amplitude is doubled. Two things happen. You can write them in words and you can draw them out. If your drawing is not that flash, express in words. Communicate somehow. Anything is okay except sign language. Okay? All that will work. Yeah. Same questions. All right. Just aware of time, so I don't mean to sound rushed, but there are some slides which are easier to understand than others. I think I've already been through a lot of this. You know that transformer equations are basically Lenz's law, or Faraday's law. The coil in the second part of the transformer, the secondary coil here, is experiencing a change of flux. The magnitude of that is proportional to the number of turns. So the more turns you have, bigger the flux going through, bigger the induced EMF, and therefore you get the transformer equation, which is for 100% efficient transformers. Okay? And then the rest of the equations here. So questions on these, I have simplified down to a wonderfully working scenario for most students in my class, which is what is the power generated at the workshop? What is the power lost? What is the power remaining? This industry is called power industry for a reason. Calculations are done in power, not voltage. So even if they say voltage loss, yes, you can do IR, but it's sometimes wrong because the resistance is the resistance of the total lines, not just over a section of the line. So what is the power generated in megawatts or whatever? Power lost, I squared R. Power remaining, the difference of those two. Divide by the current, you can get the voltage loss. All right, so here's some questions on that. And you can see power is V times I. Power loss is I squared R. Power loss is I squared R. That sort of concept will be very commonly tested. Power loss is often called I squared R losses. That's how significant it is. By the way, if any of you are interested, I have a very small sample of the world's first superconducting wire that's been used in transmission lines. Only about that big, which I brought with me from Japan. If you want to have a look, I can show you that. Okay, so there's no power loss there. It's something some of you might land up working in that industry. You don't know. Okay, here's another one. Voltage loss. Yes, you can use voltage loss occasionally, but if you use power loss, power remaining, power generated, voltage generated, you can't go wrong. I often like to follow that. Okay, so some worked examples for you to trace at home. Some conceptual questions just to take a break. So just have a read, see if there's anything in here you'd like to discuss, then I'll ask you a couple and move on. Maybe some of those are more unit 4. But why is there a force on a current carrying conductor? I hope you now understand that the force is coming from a realignment in a vector addition of two fields. That's where the force is coming from. Okay. Newton's laws I don't want to dwell a lot on because I think they are relatively simple compared to some of the stuff we have done. And these are some of the areas under which it could be tested. Straight line motion, projectile motion, circular, and satellite. And we've already touched on many of those concepts. My suggestion to you would be make a list of the concepts. It'll take you a few minutes to do. Momentum, energy, components, uniform circular, weightlessness, etc. And that's your paper. That's your final exam. One question on each. And if any of those concepts are not clear to you, please see your teachers and say, I want to understand why that happens. Because just memorizing equations is not what a KLD scholar should be doing. Okay. Here are some concepts of straight line motion expressed graphically by equations. These equations are nothing more than mathematical interpretation of graphs. Don't have enough time, but I'll just show you one on how you can derive these mathematical expressions. Okay? Let's say something starts with a speed u and goes to a speed v in straight line, and it does so in a time t. What is the mathematical equation of this line? Y equal to mx plus c, isn't it? So y is equal to mx plus c. What does that tell you? V is equal to u plus at. That's what it is. Calculate this area. What is it? It's the distance traveled, the displacement. If you did that, you get ut plus half at squared. So all those equations are not magic. They come around from converting graphs into mathematical expression. You're only doing this for straight lines. Think about what happens in three-dimensional curved spaces, especially three-dimensional curved spaces that are varying with time. That's what physics research is about right now. I've got a project where I've taken a very small, I won't go into it, never mind, but it's terabytes of data coming through. Where not only things are moving in 3D, but the space is also moving. So you get a four-dimensional mathematical regression trying to figure out a quantum magnetic dipole. Terabytes per week. Go for it. Straight line motion, some other concepts in there: impulse, momentum, and collisions. Impulse is change in momentum. Momentum is a vector quantity. Whenever you're doing questions on momentum, please don't forget to include directions. In fact, that should be the first thing you do when it comes to collisions. When estimating acceleration, remember it's net force over m. These are vector quantities. Always use the sign convention in your working. Always check units, and I have a question here that can hone in on some of those things. This was a question, I think, that I showed last year. No, this is 2018 exam. And in the KLD lecture in July, I did this on the board. I had no idea that it was going to be in the final exam, but it fronted up. Now, in July, right? It's July. Yeah, in July last year, I showed the working what a free body diagram is. I want to do one question now to show you a free body diagram. If it fronts up in the final exam, honestly, I don't know. All right, I'm just going to do one to show you how it could be done. I'm sure you've done this already. Let's say there is an object here. It's at 30 degrees. It's got a mass of 8.0 kilograms. There's a pull up here through a pulley. And this mass is, let's say, 12.0 kilograms. I'll call this A, I'll call this B. And there's a friction force opposing all this of 9.0 newtons. Now I've got two questions for you. What is the acceleration of block A? And what is normal force for the apparent weight of block A? For that to happen, you can draw two free body diagrams. There's A and there's B. What are the forces acting on B? You've got 12G acting down, and you've got the tension acting up. And notice the tension force is smaller than the one at the bottom, because the whole object, all of that is going to move this way. On A, you've got tension pulling it up, and on the downward force, you've got 9 plus 8G sine 30 degrees. And in the 90-degree line, you've got mg cosine theta this way, and the normal force that way. The components must be drawn with dashed line, and real forces with solid lines. So if you're not clear about these, just make sure you do that. So if I have to draw a component of a vector force here, I'll be drawing that with a dashed line. Normal force is the real force. The weight component here, which is mg cosine theta, is dash, normal force is real. Should be with a solid line. Now you got these situations, and you can go net force equal to ma. So 12 times 9.8 minus t is 12a, and t minus 9 plus 8 times 9.8 sine 30 degrees is equal to 8a. You got two equations here with two unknowns. You can solve them simultaneously. And what's the fastest way of solving that? Add them up. T's will cancel, you get the acceleration. It's the least stressful, most methodical way of doing multi-body diagram analysis. Look it up, it's called a free body diagram. I've got a worksheet on the internet somewhere on free body diagrams. Some student of mine put it up there. If you can find it, use it. It shows you, I think it's got a YouTube clip of mine in there explaining this as well. So if you can find it, great. If you don't follow vector arrows and directions properly in here, you will make errors. So it's very important to show which way you're looking at positive. Look at the methodology that I've shown here of free body diagrams. I think there could be a couple more questions here as well. Same thing here, the use of components. You notice the resultant force, mv squared on r. In this particular question, net force is towards the center. It's not a real force. It's a mathematical addition of different forces. Therefore, we show that with a dashed line. The real forces are shown with a solid line. Okay? Right, moving on. That's the thing I just drew for you. And then projectile motion. Now, there are these equations in projectile motion that you have in your formula sheet. Please keep them. They're good. But that's not where the questions are in VCE anymore. These diagrams are from VCE, this one, but that's not what we use most of the time. What kind of questions are asked now are these. So something is launched at 30 meters per second and it hits this board. So you can't use those equations you've just done. So what do you use? You can use horizontal and vertical components, and that's your checklist. Make sure they're vector quantities. Must have the right direction with them. Signs. Acceleration is constant only downwards. There's no acceleration on the horizontal direction. So you can start using components, and I think I have a word solution somewhere. Here we go. I suggest this to my class. Draw a line, vertical line, horizontal motion, vertical motion. Put an arrow in here with a circle. So that's positive. And suddenly you have identified what is it you're doing. You're solving horizontal motion independent of the vertical motion, and you have allocated the positive or negative signs as they should be. Just one line will do the trick. And then it doesn't matter which one you analyze first. So in the horizontal motion, x is equal to 26 meters given to you, and you can work it out. In the y direction, you can work it out. Is that okay? I presume you're following these sorts of methodologies. If you have one that works, use it. But this is the one that works for me. So if you're standing at the edge of a building and you toss something up, how long does it take to hit the ground? If you use, vector notations for it, a lot of things will become quite simple. And similar questions here. This is 2013. Something is launched like that. This is something I would love to see this year in the final exam. And please don't come back next year and say, how did you know? I don't know. I'm just guessing. So something is launched at 20 meters per second. How long does it take to hit the sea? And you have to use vertical and horizontal components. Horizontal component 20 cosine 30, okay? And vertical component 20 sine 30. If you call that plus, this would be minus, g would be minus, and you can work out what time it takes, multiply by the horizontal component, you get the range. So separate horizontal and vertical analysis. Free body diagrams to do this. This is a VCAA question. Calculate the magnitude of tensions. Now you've seen what a free body diagram can do. Put that in here. You have plenty of space. Work it out. Okay, and you can check your answers from the 2013 VCE paper. And these are some suggestions for you to think about, which I have already mentioned. Circular motion is relatively simple. The fact that the net force is mv squared on r makes things really, really easy. Why do these, have you all been on these vertical loops sort of thing? Yeah? Why are they not perfectly circular? They're all sort of closed, you know, they're elliptical. And the reason is this: at the top, right at the top, the weight is acting down, the normal force is acting down, and the addition of those two is mv squared on r. So the limiting case is when the normal force goes to 0. If I cross that out, v is equal to square root rg, something that you would see over and over again in this course, v equal to square root rg. That is the minimum speed you must have. If you go at that minimum speed, you will fall down. So you have to go higher than that. The moment you go higher than that, you're no longer in uniform circular motion, and therefore those tracks are elliptical. It allows you to speed up at the top for the safety of the driver, and more importantly, the safety of those motorcycles. They're very expensive, okay? So they have to do that. These diagrams here, weight's acting down, normal force is acting up, the difference of those two is mv squared on r. You notice the arrow at the bottom is bigger than the arrow at the top. The arrow at the top here is bigger than the arrow at the bottom, because n minus mg is mv squared on r. I should have written f subscript n, but that's okay. On banked surfaces, this is the normal force, this is the weight acting down. That, I don't know what happened to that little wheel, it should be touching the ground. Please do that in your notes. And the net force is towards the center. Net force is towards, it's not going down the slope, it's towards the center. So as if the vehicle is up in the air about that far. The center of gravity is about that high above the road and is going around in a circular path. The net force will be towards the center of the circle. That's n cosine theta is mg, and n sine theta is what provides the normal force, mv squared on r. So if you want a higher speed, you take a higher angle, and that's why you bend towards, you know, on your bicycle so you can, or a motorbike, so you can get a higher speed. And once again, the component v is square root rg, in this case, times tan theta. So these equations are all here. I've shown the working, and I think I have a question or two here, yes? So you can go through these questions in your own time. Special relativity, I think we can just remember it's a very small part of the course, so please don't think it's something really big and you got to spend weeks analyzing that. Time dilation, length contraction, energy considerations. 3 points. What you have to be clear about is what's proper time and what's relativistic time. What's proper length, what's relativistic length. If the start of the measurement and the end of the measurement are in the same reference frame, it's proper. So if you're measuring the length of this room, that's event 1 measuring there, that's event 2 measuring there. The two are in the same reference plane, proper length. That's the important consideration here. And also, keep this in mind. If you're sitting here and a spaceship goes by, that spaceship will appear contracted to you in the direction of motion. That's it. Not any other direction. So the window will become shrink, just in that direction. Harry Potter had it wrong in one of those episodes when the bus goes very fast and it becomes slim. You remember that? And also becomes longer, and wrong physics. It's only in the direction of motion. Now Sheldon had it right in many episodes, but no, not that movie. So it just shrinks in the direction of motion, okay? What about time? So as long as you can understand, for example, a scientist watching a particle go by, the particle is doing the right thing. That's proper time. The scientist is measuring dilated time. And that's the explanation for muons and time dilation and all the concepts of the twin paradox. So keep those concepts clear, the rest will follow. Question about the Lorentz factor is really important. The Lorentz factor starts from 1 and goes to infinity. It can never be less than 1. If you're talking about length contraction, you're not going to go less than 1. Okay, so just be clear with that. What does the graph of the Lorentz factor look like? 1 going up. What is gamma minus 1 equal to? 0 going up. Why am I saying that? That question was asked in 2017. Okay, just the Lorentz factor. What does it look like? Oh, here it is. I've just made up those graphs just from Lorentz. Oh, this is, no, I didn't make them up. This is 2018 question, sorry. What does the gamma graph look like? A, B, C, or D? Quickly. Hint, D, okay? Goes up like that. So if you're looking at time dilation, that's the graph. If you're looking at length contraction, it would be gamma minus 1, and I think that could be the next graph somewhere. And there it is. That's length contraction, that's time dilation, and what happens to those times. Notice this graph starts from 1, not 0. Okay? These are from my class notes, I think. No, this is from Encyclopedia Britannica. There you go. Right, let's look at some questions. Again, these questions are sitting there with you, so you can explore them in your own time. The spaceship has to land in that area. So what it has to do is slow down, perfectly stop if you can, 500, and then it can just plonk down here. Because if it doesn't, it's going to find the landing strip to be much smaller. Whereas a person on this strip is going to find the ship much smaller. And so what's your problem? The ship said, no, the landing strip is too small. And we have a little run-in with that. We've done this in class. Okay, some questions here, as I said, you can follow at your own pace. Same thing here. I wish I had the time to explore all of these, but in your own formula sheet or in your own conceptual learning, put down twin paradox, the problems with the muon, the contraction of the spaceship. 3 main concepts. Okay? Make sure you understand those 3 concepts. The muon should have not made it to the Earth. The half-life is way too small. Why do we detect them? Because to a scientist, the half-life is dilated. To the muon, the length to Earth is contracted. So the muon says, I'm going to make it there because the length is much smaller than you're claiming it to be. And the scientists say, no, length is way too long, but your half-life is much longer than you're saying it is. And that's what makes it. Doesn't matter, both are right. And if you calculate the speed of the muon, it will come out to be the same in both those cases. Okay? But it's just a matter of perception. More questions here. But I just want to go through one more thing about energy. Kinetic energy is gamma minus 1 m naught c squared. That should be in your formula sheet. The total energy is not just the rest energy, but also the kinetic energy. And you put that together, the rest energy is m naught c squared, so this quantity is m naught c squared. Kinetic energy is gamma minus 1 m naught c squared. You add them up, you get gamma m naught c squared. That's the total energy. Don't need to memorize it, put it in your formula sheet, direct application of this question in your exam. Okay? So the rest energy of an electron is, rest mass of an electron is 9.1 times 10 to the negative 31 kilograms. That's m naught. If an electron is going at 99% of the speed of light, put in the value of gamma, subtract 1, multiply by the rest mass times c squared. One thing I would suggest to you guys is make a little table of gamma values. Okay? If you look up the past few years of VC exams, it'll really help. The speed is 99%, 98%, 97%. What is the value of gamma? All right? So you don't make silly errors in the exam. These are just some questions, and same thing here. I've just played around with this equation to give you some scenarios I just spoke about. In a stationary reference frame, no speed, energy is m naught c squared. Once you give it speed, it becomes gamma times m naught c squared. And then you can derive the rest. So have this in your formula sheet as well, and some questions to follow. All right? Lots of questions here. In fact, the calculation of gamma and the reverse of that. If gamma is equal to 1 over v squared minus c squared, 1 divided by square root 1 minus v squared c squared, can you make v the subject and calculate gamma at different v's? Wonderful question. If you haven't done that, do yourself a service and derive that expression. What is v equal to in terms of gamma? Here's a question on that. And yes, it's one thing I would love to see this year. Okay, at what speed does gamma become 10, 20? Does the speed double? Here's a ratio question. The gamma is double. What happens to the speed? All right, those sorts of things. I'm not going to spend a lot of time on this because this is year 10 stuff in my school, or year 11 stuff. Things like what is kinetic energy, what is impulse, what is momentum, how do you apply energy conservation on a little carriage here that goes from A to B to C. So A to B, gravitational becomes kinetic, kinetic becomes gravitational plus kinetic. Any loss of energy is force of friction times length. Is that clear? So if I tell you the force of friction between A and B, multiply that by the length between A and B, that's how much energy you're going to lose. Where does it go? It becomes heat and light and so on, and sound. So if long as you go energy at A, energy at B, energy at C, subtract the work done against friction, make it nice and neat. It's scalar quantities, no need for signs. Okay, I put this question there as one of the last things I'm going to show you, I think. I'll just have a quick check. I don't think I have plans to show you much more than this just now. So we are here. The rest I can follow in at the end of the year. Did it happen here? Okay. This question on springs. Please spend some time looking at it carefully. There are three criteria for springs. You attach a mass to it and gently lower it so it stops. Look at the words I've used. Gently lower, stationary. When that happens, forces are balanced. So mg equal to kx. Case 1. Case 2. If you gently allow it to oscillate, then it goes through gravitational to elastic through kinetic energy. Energy is conserved. If you just drop it, or if you pull it, then you've done work on it. And when you do work on it, then all those equations fail. Now, all of those things have been asked in VC and will be asked again this year. Gently lowered and stopped, mg equal to kx. Gently lowered and oscillates, mgh equal to half kx squared through half mv squared. And if you do work on it, then everything else fails. The expression at the bottom here is really useful. That tells you at midpoint what's happening. So let's pause very quickly. 3 minutes, I'll be done. Gravitational energy at the top. The mass goes all the way to the bottom, becomes elastic energy. So elastic energy is maximum. Elastic energy follows a curve. If you add these energies, they won't add up because there's kinetic energy as well. Now all the energies will add up. So if you add that quantity plus that quantity plus that quantity, you'll get a flat line here, which is conservation of energy. So what is the expression for this particular line? Okay, that's an interesting question. But also, at the midpoint, the total energy, which is mgh, which is half kx squared, should be equal to mg, half the displacement, half k, half the displacement squared, plus half mv squared. And that tells you how you can calculate the maximum speed in the middle. This is 2015 and 2017 and possibly 2019. Okay, so please make some time reading my working out here. I'm not saying this is the best working, but it'll get you there quite comfortably. Any questions on this? Okay. Now this bit here about accuracy, precision, uncertainty, and error is useful for your EPI, so I've put it in there, but I'll discuss this in September with you. Okay? And here are some more questions that I want you to explore, and come back in September if you have any questions. Right? This is just an interim session we're having here. Okay? Now, 24th of September is when we meet next. And by then you'll finish the course, have your dinner, dance, and valedictory, whatever stuff you go through, and we can come back and with questions to ask me. We are right on track. I think we finish at 12:30, am I right? So we have 2 minutes to go. If you have any questions. Yeah, sounds good? Okay. So look, what I've tried to do is give you a feel for what the course is, what could give you sort of good performance in the final exam, what sort of things you should be looking for, methodologies, signs, whether they're vector quantities, scalar quantities, numerical calculations, putting the equation there, real simple, systematic, logical answers. So hopefully you've picked up a handful of points to get the good scores that you deserve. All right? That should be good. If you need to contact me, I think probably the best way is through Michaela, but I do teach at Scotch College, and maybe that's one other way of finding me. So my name is there in your form, in your notes, and you're welcome to contact me. Okay. Enjoy your pizza. I think that's what lunch is. All right. We'll see you in September. I will be around at the pizza place lunchtime session if you have anything, or I'll stay around briefly at the end of the day as well. All right? Okay. See you. Good luck. Sure.
So with the kinetic or kinematic equations, you were describing it with graphs and stuff.
Yeah.
Could you explain that to me again? Because
Yeah.
I've never seen it before.
Come on here. So for example, this one, is what you're referring to?
Yeah.
There's an object that starts with speed u, goes to b at uniform acceleration. The acceleration is the gradient. So you can graph it like that. What if you take a ball with the edge of a building and toss it up? So you have a certain u, final speed could be 0, or maybe it's hit the ground, doesn't matter. That's where you are. That could be rapid motion.
So does that only work for uniform?
Only straight line motion.
Yeah.
And only uniform motion with acceleration.
Okay.
Because then you can go y equal to mx plus c. Y is v, if you like.
Yeah.
M is the gradient. X is time. U is here.
Okay.
And you can just get that.
All right. Thank you.
So a lot of these straight line equations, I've actually got the original version of Newton's book in Latin.
Oh.
And he has
Have
drawn.
you read it?
Yes, I have.
Can you speak like read?
I can. Not, I can't speak Latin myself,
Yeah, yeah.
but I studied Latin in German.
Oh, okay.
So yeah, you can follow the graphs. You've got that. It's not
Okay.
You've actually got that one.
So can you use it for most of the kinematic equations?
100% of them.
Yeah. Oh, wow.
So if I ask you a question, what will the graph look like if a ball tossed up
Yeah.
at the edge of a building? So you're starting with here, and you toss a ball up, and you say going up is positive. So running out of space. You start with the speed here, initial speed.
Yeah.
It's going to do that. And the gradient is g. That's when it hits the ground. That's when it reaches 0 speed. This is v versus t. Always draw velocity time graph. Very handy. Gradient is acceleration. And the area is displacement. So that area of the rectangle tells you how far it goes up. That area here tells you how far it goes down.
Oh, that's cool. Okay. Yeah. Right. Thank you very much.
Yeah. So drawing a velocity time graph is always the best way.
Yeah. No, I've never been.
Questions like what happens if a policeman gives chase, etc., etc.
Yeah.
All based on velocity time graphs.
Okay.
Which school are you in?
Melbourne. It's public school in
Oh, that's great.
Brisbane.
Yeah.
But yeah, it's my teacher's first year teaching physics.
There's a difference.
Yeah.
And anybody I think maybe in my first year I would have done this.
Yeah.
This is my 30th year, so it's a different story.
Yeah. You learn so many things.
Yes.